we have a use case for an e-axle development project, and understanding the lubrication between, the gearbox side and the motor side.
Yeah.
And making sure that we can optimize that for a super wide range of conditions. So not only do we need to be able to consider the speed of the motors, or the speed of the gears, and how that is, churning the fluid around, but also looking at a wide range of vehicle maneuvers. So where is that sloshing going to happen? A wide range of temperatures. Viscosities of these oils can change an order of magnitude over cold start to really warm running. So there's a huge difference in the way that the fluid will behave over that range. And being able to robustly look at a much wider design space than something that time would allow us to do in a testing environment is a huge benefit, and then not only that, being able to look at all of those design points, but also being able then to consider different design variations, whether or not we should put the baffle here or there, how large in diameter that drilling should be to provide a certain flow rate, being able to optimize features not only for overall performance, but also to meet performance targets at specific operating points. So at high speed, you have a certain, angle in this deflector, which makes sure that you provide extra lubrication there, just based on, oil only gets sloshed to even be interacting with that deflector once you get to the high speeds. So being able to provide design features that do certain things only at certain times in a passive way, rather than being actively controlled. We can also talk about active control, but being able to build in those passive design features, I think, is something which would be really difficult to do in a traditional testing environment, especially because you can't really see what the lubricant is doing in those cases. So I think, the scale of testing that we can do in support of development is a huge advantage. And also thinking about, some of those other edge cases. Of course, we historically have focused in mobility, automotive, and transportation industries. And that's, the lifeblood or the history of AVL. But that industry is changing so quickly, and there's so many new players, and that landscape is shifting faster than it ever has before since it started. And one side effect of that is, we're getting exposure now to a lot of other use cases and a lot of other places where this kind of technology could provide a huge benefit. And CFD is used in all sorts of industries, but one place that we've been looking recently is in white goods, or commercial goods, or consumer goods, I should say. And looking at, for example, dishwasher applications. And in a dishwasher, I don't know. Sometimes the simplicity of the setup is misleading, right? Because we think about a dishwasher as something that you interact with every day, and it just works. But there's a huge design task that goes into that. Like how fast should those arms be rotating based on the water pressure that's available? Are they providing enough pressure and enough shear stress on the surface of the dishes to wash off your crusty old casserole from 2 nights ago? And always coming back to the age-old question of, is there a right way to load the dishwasher? I think if we can answer that question with data, it's a bigger, we're looking at the bigger questions here, not just the engineering stuff, which is pretty exciting. And we can answer that now. So with PreonLab, we have a lot of studies for, that jet targeting, how the nozzle should be targeted. We can map out the shear stresses that each of the dishes experience. So are you going to have a situation where your ketchup isn't washed off all the way? Or even is some of it, sometimes it's too much, and it flips over the lighter plastic Tupperware that you put in the top drawer. or the bottom drawer because you are a rule breaker and a rebel and you just put things where they go. But how, putting some engineering data behind that and being able to simulate new things that I think have been difficult before as well, and including multi-phase. Can we actually simulate the ketchup as well as the water? And is the jet, if you put the dish in the slot which is closest to the rotating arms, is it going to be that like the ketchup's actually going to spray up and get other dishes dirty that weren't dirty before? And so looking at some of that secondary soiling. So yeah, I think there's a lot of crossover to new applications, but some of the same questions. We answered the same secondary soiling question when we were looking at ADAS sensor soiling, and understanding how droplets are being generated, and if they have a secondary contact then with the vehicle. It's some of the same tasks that are happening inside the dishwasher as well. And one really cool application that we're thinking about now is really high viscosity materials. So things like peanut butter or really pasty, gluey, nasty things. And can we simulate some of that? Looking at some of those fluids, the viscous forces inside those fluids are so high that computationally it was just a huge effort, because you had to take super, super small time steps in order to understand where the fluid was going. And with PreonLab, we offer an implicit pressure solver, as well as an implicit viscosity solver, which allows us to speed up some of those calculations. And now we can look at, shampoo or honey as it's flowing around. And one application that we're looking at now is squeezing of thermal interface paste. So when you have a battery module as an electric vehicle, and then it's being installed into a pack of multiple modules, there is a thermal interface paste that goes in between the module and the housing. And that allows for good thermal contact. First off, it's an adhesive, so it fixes the thing in place. But it also allows for good thermal contact between the pack itself and the module, the battery module, and then ultimately the cooling plate, which goes underneath the pack. And what that means is that ideally you have a homogeneous temperature within the module, but also within the entire pack. And that, prevents any kind of this cell-to-cell balancing kind of issues that might happen. But also it's ultimately a longevity thing. If you have big temperature disparities or discrepancies within that system, then you can start to see premature aging. And then we're not meeting lifetime expectations that we should. But on the manufacturing side, practically, when you apply this stuff, so you squeeze it out into a certain pattern, then you take your module, you squish it down, and exactly what you think is going to happen, some of it squeezes up out of the sides, so you need to have enough that it has good contact underneath the module. But if you put too much, then your layer is too thick and it's not as conductive as you hoped it would be. But also you have all of this waste that's happening, which is something that we could maybe try to optimize or minimize. So the question now for simulation becomes, not only can we simulate that squishing effect, that squeezing effect, that squeeze out losses and the wet out, but also, how can we approach that in an engineering way? So is there an optimal pattern for that paste application? How much exactly paste should I apply? Am I going to have to push really hard on the module and potentially do damage or deflect something for thin parts? And understanding, what's the best way of doing this seemingly simple task of putting paste in between two components and squeezing it out. But, there's an opportunity there for, not only making sure that the components are going to work as they were designed to do for as long as we expect them to, but also on the manufacturing side, reducing those losses, reducing that total material, and making it come together as fast as it can,